Right. Is it visible now? Visible, right? Okay, screen is visible. Right. Listen about electronics and the first essay question we are going to discuss. Right. First part of this first essay is from FETs. Right. First part is from FETs. Right. I will quickly recall the background you should know about FETs first. Right. Quickly, and you will get to know the other things. Right. Other things means the special things and the additional details. Right. Additional details. Uh, as this goes, as the discussion goes, right? Api discussion natin carry walong. All right, then let's see. First thing about FETs. FETs means field effect transistors. No? When it comes to FETs, you have two types, right? FETs. There are two types of FETs we have. One is NJ FETs, right? NJ FETs, N channel junction field effect transistors, and the other type PJ FETs, right? PJ FETs, P channel junction field effect transistors, right? NJFET and PJFET. Now, from these two, when it comes to questions, you are getting only questions in the sense for calculations, for sums, right? For sums, we are only getting from NJFET, right? From NJFET. So, quickly, if I recall, NJFET is something like this is the circuit symbol. Circuit symbol is like this, right? And this common terminal is called gate, and this is called drain, this is called source, right? Drain, gate, and source. And current flows here are, right? Current flows here, there are only two current flows. ID flows downward and IS flows downwards. There are no currents in G. There are no currents through G, through gate. And usually gate is grounded. Usually gate is grounded unless there is a voltage divider circuit. In voltage divider circuit, gate is not directly grounded. It can be different with the voltage, right? Actually, in this particular question, what is given is a voltage divider circuit, right? There is a voltage divider circuit. Since there is in the question, I will explain the other things about the voltage divider with that, right? And here, one more thing, since there are only two currents, always ID equals IS about ID equals IS about a NJ FET, right? Or any kind of a FET circuit. ID equals IS, right? Now, let's start. Let's start about the first one, part A, right? First question, it's asked, why field effect transistors FETs are called unipolar devices? What are the charge carriers contributing to the operation of FETs? Right, unipolar. Unipolar devices means they operate only with, or they function only with, they work only with one type of carriers, right? One type of carriers. In electronics, we have two types of carriers, no? Right? In electronics, we have two types of carriers, either electrons or holes, right? When it comes to bipolar transistors, if I compare this, when it comes to bipolar transistors, right? Bipolar, you know, NPN and PNP. When it comes to bipolar transistors, they have majority carriers and minority carriers, right? Which means both carriers are contributing. Uh, the functioning of the transistor, right? Or the operation of the transistor. When it comes to unipolar transistors, uni means one, no? Uni means one. That's the exact meaning. Uni means one. Then here, only one type of carriers. It is either electrons or holes contributing the operation of this FETs, right? That is why they call unipolar, right? That is why they call unipolar. Then what is asked is why they are called unipolar transistors. Then you have to say that, right? Because either electrons, either electrons or holes, because either electrons or holes are used as electrons or holes are used as carriers for the operation. Unipolar means one type of carrier is used, and other than that, there's one more thing in bipolar transistors. There are two p-n junctions, but in unipolar transistors there's only one p-n junction. In bipolar there are two p-n junctions, right? In unipolar there is only one p-n junction. There is also another difference, right? Main difference we can see between these two. The main difference is this one, and the second main difference is about the number of PN junctions. Okay, then what are the charge carriers contributing to the operation of FETs? Right. Then for the first one, they are not asking for the electrons or holes, right? Then you are mentioning, if you have mentioned about just as only one type of carriers are contributing, that is enough. That would be enough because only that is asked, right? Because either electrons or holes are contributing. Then for the second one, you can write as what are the charge carriers contributing to the operation of FETs? That is either electrons or holes. Either electrons, or holes. Either electrons or holes. Right. Now, without writing or without mentioning specifically about electrons or holes, if you mention that just as one type of carriers, that is also enough as how it is asked in the question. Right. Second one, state why FETs are also known as voltage control devices. Right. Here, the main difference is with again bipolar transistors. Bipolar transistors are called current control devices. Bipolar are current control, and unipolar are voltage control. The reason is this is controlled by VGS. What is VGS? VGS means voltage difference between, or the potential difference between gate and source. Like this, whole device is controlled by VGS. Right? Then write down this way. Device is controlled. Device is fully controlled. Device is fully controlled by the voltage difference. By the voltage difference. By the voltage difference between gate and source, right? That is called VGS. That is called VGS in our jargon. Right? In our jargon, we call it VGS. Right? Then third, calculate the drain current ID. This is the calculation part here. Calculate the drain current ID and the gate source voltage VGS for the circuit shown in the figure 1, assuming VD equals 5 volts. Assuming VD equals 5 volts. VD equals 5 volts. Now, this is D, right? This is D, and this is S, right? We know this is G. If this is G, this is VG, right? Then, if I mark the currents, ID falls downward, close downwards, and IS is downwards, right? And since it's a voltage divider circuit, this is called a voltage divider configuration or voltage divider circuit, right? Then if this current is simple, like let's say no current inflows through G, then it flows like this, right? Then we can say same current flows through, right? Same current flows through what we call R1 and R2, and they are in the series combination. That is also noticeable, right? And what we need is VGS. VGS is here. Potential difference between G and S is here, right? Now, what we asked is ID. ID first. ID and VGS. To find ID, now VD is given. No, VD was 5. See, VD is given. This is 5. Then about RD, potentials at the two terminals of RD of the resistor connected to D is known, right? Which means you can apply delta V equals IR for resistor RD, right? Then this one, number 3, what we can do is for resistor DRD, delta V equals IR, right? Delta V equals IR. Then delta V is high potential to low potential 9 minus 5 equals ID RD is 2.2 kilo ohms kilo, right? Then that's a small simplification. ID equals 9 minus 5 is 4, then 4 over 2.2 10 to the power minus 3. 4 over 2.2 is 1.82. 1.82. Then this is 1.82 milliamperes. 1.82 milliamperes, right? The other beauty of FETs is, right, all FETs are simplified, or they are done, they are solved using mainly using delta V equals IR, delta V equals IR or V equals IR, right? As specific equations for a FET, we have only one, that is also only for the normal configuration, not the voltage divider. For this configuration, all the questions are solved using V equals IR only, right? Then as a second part, it is asked about VGS, right? Then to find VGS, right? To find VGS, first we need VS, no? Right? VS and VG. Then to find VS, we can apply delta V equals IR again for RS, right? For RS, delta V equals IR. Delta V across RS is, right? Now, if VDD is given here, this terminal is grounded. If VDD is given above, this is grounded. Right? Grounded means it is 0. Then this point is at 0. Then VS, we need VS, that is VS minus 0. IS is same as this, right? Same, I told you before, 1.82 milli 10 to the power minus 3, 1 kilo ohm, then 10 to the power 3. And you better mention this logic here. Always ID equals IS. ID equals IS, right? Then these two cancels off. VS equals 1.82 milli, sorry, VS equals 1.82 volts. 1.82 volts. 1.82 volts. Then I need VG. To find VG, what you can do is these two resistors are in a series combination. Right? I have to mention these logics. Mention these logics. R1 and R2. Right? Mentioning logics. Right? Is a must you should do. It's a must thing you should do. Right? So even though you are doing the question, right? If you miss mentioning these logics, you will lose marks. That's the thing. Right? Mention these things. R1 and R2 are in series combination. Are in series combination, right? The reason is Ig equals 0. Reason is Ig equals 0, right? R1 and R2 are in series combination. Then using voltage divider, that is also called potential divider. Using voltage divider for will apply for the grounded one for R2. Then total potential difference across that branch is, if this is VDD, same wire up to here, this is VDD, that is same wire, then that is 9. Then if this is 0, same wire up to here 0, right? Then total potential difference is 9 minus 0. Total potential difference is 9 minus 0. Potential difference across my resistor is VG, then VG minus 0. Total is VDD minus 0 over R1 plus R2 into R2, right? Apply the values here. VG, I need to find VG, right? VDD is 9 minus 0, that's 9, no? R1 plus R2, 10 plus 2.2, 12.2, no? 12.2, right? Times 2.2, right? Simplify this, right? Simplify this. Then it is coming as 1.62 volts. 1.62 volts. Now our target was VGS. Our target was VGS. Then you can write VGS now. VGS equals VG minus VS. Right? VG is 1.62 and VS was 1.82. 1.82. Right? VGS is minus 0.2. Minus 0.2. Right? In any kind of a FET, VGS is always minus. In any kind of a FET, VGS is always a negative value, a minus value. Right? Then this is also a verification that you should get a minus value. Right? So we have got a minus value. Right? Kind of a verification. Right? So part 1 is done. And this part was given for 10 marks. This part was given for 10 marks. Right? That's nothing much to do, right? But 10 marks are given. Right, part B. Part B. Now, part B is about op amps. Part B is about op amps. Right, now in these selected questions, right, kind of target questions with a high potential this time are here, right? So that's why I'm discussing these ones, right? You better check these question types again and again and practice these question types again and again before you go to the exam, right? Different question types we have here, right? Analog, digital, bipolar transistors, unipolar transistors, then op amps, diodes, Zener diodes, right? Rectifications, okay, circuits again, right? B. In the op amp circuit shown in figure 2, each electromechanical switch SI, I equals 0, 1, 2, 3, is operated by applying an electrical signal DI, I equals 0, 1, 2, 3, right? Which can be high 5 volts or low 0 volts, right? High means 5 volts, low 0 volts. When DI is high, the respective switch SI will be closed. When DI is high, DI is high. If DI is given a high signal, if DI is given a high signal, right, then the respective switch is on, is closed. Closed means on. Otherwise, it will be open, right? Okay, then first one. Oh, wait. Sorry, the question is missing here, it seems. Some part is not clear. That's an error occurred with the compiling, right? Compile කරද්දී මේ part එක වෙලෙන්ට දාලා නැහැ වගේ. What's the question? Yeah, a small part is missing. So I will read out the question and we'll do, right? And this is actually 2019 level past paper question, right? Check the given questions with the past papers you have, right? Right? Check the given questions with the past papers you have, right? මෙතනින් පස්සේ තියෙන questions ටික මේකේ වැදිලා නැහැ. Yeah, that is not clear. It's a mistake, typing mistake, right? Question one is asking, when D2 is high, find the current through the resistor 10R in terms of R. When D2 is high, right? Listen, D2 is high means D2 is on. Now switch D2 is this. D2 is connected to S2. Now this is going to be on, right? When switch on karata, D2 is going to be on, right? And the current through resistor 10R is asked. Current through resistor 10R is asked. Current through resistor 10R is asked. Right. Now, see what's happening. Now this is given as -5. This is given as -5 here. -5. Then if there is -5, this is the same wire. This is -5 here, up to here. Right. And this is grounded. This is grounded. So we know we have golden rules for op amps. Golden rules. Right. One golden rule is there are no current inflows through the input terminals. There are no current inflows through the input terminals. One golden rule, right? And the second golden rule is if the op amp is feedback. What is feedback? Feedbacking means if the output is connected back to one of the input terminals of an op amp, that is called feedback, right? That is called feedback. If the op amp is feedback, V1 equals V2. Right? If the op amp is feedback, V1 equals V2. V1 is the notation for the non-inverting voltage terminal +1, right? And V2 is the notation for the inverting voltage terminal -1, right? Then if this is 0, this is a feedback circuit. Since there is a feedback circuit, if this is 0, V2 is also 0 because in a feedback circuit, V1 equals V2, right? You have to mention these logics. They are the logics, right? These are the logics that you are given marks, right? These are the logics you are given marks, golden rules, right? You have to mention, right? First golden rule, you have to mention it when you are answering, right? First golden rule, you have to mention that there are no current inflows. There are no current inflows through input terminals. There are no current inflows through input terminals. So when we write all of them at the beginning, that is easier. Right? Otherwise, with the question or with the part that you are trying also, you can do. Right? But when you have written everything at the beginning, then again you don't need to write it again and again. That's it. There are no current inflows through input terminals. Right? And the second one, V1 equals V2 when Op amp is feedback, right? These two are called golden rules, right? These two are called golden rules, right? Now, for this one, I have to use V1 equals V2 thing. Then V1 equals V2 equals 0 volts here. V1 equals V2 equals 0, right? The reason is golden rules. The reason is golden rules, right? Now check the circuit. Check the circuit. Now this side is at 0, right? This side is at 0. If this is 0, V2 is also 0. This is 0, right? This is 0. Now, what's the question asked? Current through resistor 10R. Current through resistor 10R. Now, if this is 0, this is the same point up to here, that is 0. Then potential difference across 10R is known. Apply. Delta V equals IR for 10R, right? Then for 10R, apply. Delta V equals IR. Delta V equals IR. Delta V is now current flows in this direction from high voltage to low voltage. Then potential difference is 0 minus minus 5. 0 minus minus 5, right? Otherwise, you will get a minus current. That will be wrong. Then let's say that current is I, R is 10R. Then I equals 5 over 10R, right? That is 1 over 2R. So the current is 1 over 2R. One over 2R, right? Next, if a set of voltages, second one, see, if a set of voltages 5 volts, 0 volts, 5, 5, which means 5 means high, no? Right? 5 means high. Simultaneously to operate switches S3, S2, S1 and S0. Right. Now, this operation changes. See, now this operation changes. Now again, you have to check what are the switches that they are going to be on and what are the switches going to be off. Right. Now we have to check what are the switches going to be on and off. Right. Let's see. Okay. See. Now 5 volts is given for S3. Then S3 is on. S3 is on. And 0 for S2. Now S2 is closed. And the other two are also on. S1 is on. S0 is on. S1 is on. S0 is on. Right. Then what is asked is calculate the current capital I indicated in the figure. Right. Now what we know is, right, there are separate current flows through these ones. No, say this is I3 and say this is I2 and say this one is I1, right? Then we know from Kirchhoff's laws this capital I is I1 plus I2 plus I3. Then if I find I1 plus I2 plus I3, right, one way is you can get that capital I. That is one way. Or else the other way is we can clearly see these three resistors are in a parallel combination. These three resistors are in a parallel combination. Right? These ends are at -5. And all these ends are, if V1 is 0, V2 is 0, no? All these ends are 0. All these ends are 0. Since they are in a parallel combination, first I'm going to solve this equivalent resistance. That is easier. Right? Now, without doing the equivalent, if you found the currents separately and if you do that way, that is also fine. That's up to you. I'm going to solve the equivalent. Right, then 1 over R equals, now functioning resistors are 1 over 5R plus 1 over 20R plus, right, they are parallel, no? 1 over 40R, right? Then 1 over R equals, right, so this is R dash equals, common denominator is 40R, 5 times 8, 20 times 2, this is 1, right? Then R dash equals 40R over 11. R dash equals 40R over 11. Equivalent is known. Now for the equivalent resistor, you can apply delta V equals IR. That is easier for me, right? For R dash, for the equivalent, delta V equals IR, right? For the equivalent, delta V equals IR. Delta V is 0 minus minus 5 again, right? Same thing, 0 minus minus 5, right? Capital I. Now the total current is coming at once because I'm applying the equivalent resistance. R is 40R over 11. 40R over 11. Then this is 5 equals I times 40R over 11. 5 times 8 here, right? Then this I equals 11 over 8R. 11 over 8R, right? 11 over 8R. 11 over 8R, right? Next, calculate the output voltage V out when a set of voltages 5, 5, 5, 5 is applied simultaneously to operate switches, right? If all are 5, which means all switches are on, no? Right? If all are 5, the meaning is all switches are on. If all switches are on, all resistors are going to function now, right? Part 3. If all resistors are going to function, now the equivalent changes again. Right? Equivalent changes again. Now this is also going to be on. Now I need the new equivalent, right? I need the new equivalent again, right? Say 1 over R double dash, that is given by 1 over 5R plus 1 over 10R plus 1 over 20R plus 1 over 40R. Now again, common denominator is 40R, right? Common denominator is 40R. This is 8 plus 4 plus 2 plus 1. Then R double dash is 40R over, right? 8 plus 4, 12. 8 plus 4 is 12. 8 plus 4 is 12. 14, then 15, no? Right? So that is 40R over 15. 40R over 15 is by 5 it cancels, right? 8R over 3. That is 8R over 3. Right? 40R over 15. Now that is 8R over 3. By 5 it cancels. 5 times 8, 5 times 3. Right. Now, again, for that equivalent, we can use the same thing, delta V equals IR. Then for R double dash, delta V equals IR. Still delta V is 0 minus 5. Voltages are unchanged, right? Potentials are unchanged, voltages are unchanged. Then 0 minus 5. We need this current into new R. R is 8R over 3. 8R over 3. Right? Then now from this we can find the current. If the current is known, right? If the current is known, we can find V out, because my final target is finding V out. It is also about calculate the output voltage V out. If the current is known, now I is 15 over 8R. I is 15 over 8R. Current is known. Then what you can do is to get V out, apply delta V equals IR again for 8R. Delta V equals IR, right? For 8R. Then through 8R, this is how this current flows. Right? From high voltage to low voltage. Then V out minus 0. It should be written as V out minus 0, right? And current is 15 over 8R. Into R is 8R. 8R to 8R cancels. Then V out equals 15 volts. Final answer. Right? V out equals 15 volts. So again, not a big deal, right? I'm just applying delta V equals IR accordingly, right? Just applying delta V equals IR accordingly. When you do a question from op amps, right? Must know thing is golden rules, right? Right? So without knowing golden rules, you can't touch this question, right? I recalled you the golden rules, right? These are the golden rules. There are no current inflows to input terminals, right? That is one, because resistance is too high at the input terminals, right? We discussed in the theories clearly. And if the op amp is feedback, V1 equals V2, right? Golden rules. And how to use these golden rules accordingly when solving questions, right? How to use the golden rules accordingly when solving questions, right? Then the next part here, part C here is given in digital, right? That is a digital part, digital given, or the digital question is given. A cash operated snack dispenser will provide the pack of Mari or chocolate cream biscuits under the following conditions, right? First one, the correct amount of cash is inserted. I. Mario chocolate cream is selected. MOC. Right. If Mari is selected, availability of Mari in the dispenser. If chocolate cream is selected, availability of chocolate cream in the dispenser. Why? Right. First one. First one. Obtain the logic expression. The logic expression for the conditions under which a pack of biscuits may be obtained. Right. A pack of biscuits, no? Which means now with these words, get the idea. With these words, get the idea. A pack of biscuits means that is about Mari or chocolate, no? Mari or chocolate, there is a O connection. Right? O connections. O connections are plus connections. O connections are plus connections. Then I need to focus on Mari or chocolate. Right? First, let's see the conditions that I need to satisfy to obtain Mari. Say FM. Right? Output that I need to obtain Mari is FM. Then to get the Mari biscuit, as the first thing you have to insert money. Right? Have to insert money. I have to insert money. And Mari should be there. Mari should be Mari should be selected. And Mari should be selected. And Mari should be selected. No. N means dot connections. Then dot Mari should be selected. M. Then correct amount of money is inserted and Mari should be selected. And the order you have to just check whether it is an O connection. Right? And Mari should be selected and Mari should be available. Right? O Mari should be available. Right? There's no meaning if O Mari should be available. Correct amount of money is inserted and Mari should be selected and Mari should be available. Another N connection, then IMX. To obtain a Mari, right? If IMX are satisfied, we can obtain a Mari because correct amount of money is inserted and Mari is selected and Mari is available. Similarly, if you need to obtain a chocolate cream, say FC, right? Say FC, then still correct amount of money should be inserted and chocolate cream should be selected. C, chocolate cream should be selected and chocolate cream should be available. Chocolate cream or chocolate biscuit should be available. Chocolate cream biscuit should be available. Right? Then ICY, they are connections. And about the overall output, we know we need either Mari or chocolate, O connection. Then combining these two, the final output is going to be, right? Final output is Mari O chocolate. O means plus connections. Then F is, this is IMX and this one is ICY. Right? You can see I is common, take it out. Then MX plus CY. Right? Then the final output is this. Right? Final output is this. If you didn't get this at once, you can have a truth table and check these values as well. Right? That is also a possible option. Right? That is also a possible option. But if you didn't get this at once, have a truth table and check it out. That's also fine. That's fine. Right? That's fine. But same marks are given. It will take a little bit more time than this. Right? But still you can get the correct answers. If you didn't think of it at once like this, right? Still to get the correct answer, you can use a table. Second one, show how this may be implemented using logic gates. Right. Then drawing a logic circuit, digital circuit for a given output. Right. Logic drawing a digital circuit for a given output. Then outputs are inputs are I, M, X, and CY. No, right? There are five. Then if my inputs are here, right? If my inputs are here, I, M, X, C, Y. I, M, X, C, Y. Right? So first I need IMX. Then first I need IMX. Right? I is here. Right? Take M from here. Take X from here. Right? And this is IMX. Right? This is IMX. And for ICY, the other one is ICY, no? IMX and ICY. Right? IMX, there are different possible circuits. Then for the other one, ICY, right? This is ICY. And the O of these two, no? Connect with the O gate. This is F, right? Or else, if you are plotting this for this output that I obtained here, right? Or else you can do it here. Then for this output, F is I times MX plus Cy, no, right? For that one, again, if wires are like this, sorry, if input wires are these ones, right? First I need mx, then I mxcy. First I need mx, right? There are like 4-5 possible circuits here, right? For any circuit, marks will be given mx, then mx is here, then cy is here, right? These two should be plus, then okay, and from this the addition comes out, and with I it should be dot, then take I from here, right? And you can connect an AND gate here for the dot connection here, right? That's it. So likewise, there are different circuits. There are different circuits that up to you, and for any correct circuit, total marks will be given. For any correct circuit, total marks will be given. For any correct circuit, right? That's it about that question. Yeah, that's it about that question. Right, now about electronics, the benefit that we have is you can score this in a quick time, right? You can score these marks in a quick time, right? That is the main benefit we have, right? If we are spending like say 30 minutes, 35, 40 minutes for a question like mechanics, thermal, right? Maybe electricity, right? Now in these things, in these questions, the benefit is that you can score in a quick time. You can score in a quick time, right? That's the thing, right?